Good morning, guys. It's a new day and I hope you have slept well. And now I'm gonna show you something I've done on my little PIC board. Another new thing you might have noticed is that it doesn't update for every tick. Sometimes it goes 3 times in a row, 1 or 2 in a row, or nothing. You get like a pulse train like here. Sometimes you get a lot of zeros or dark LEDs, and sometimes you get a lot of bright LEDs. And I'm using the first bit to decide if I'm going to paint or put a pixel or not. So sometimes there will be a long pause. Sometimes there will be a lot of pixels. And then I've taken these are where the pixels are going, the first 4, that means 16 pixels. And then I take the 3 next bits to decide if it's red, green and blue or a combination of these. So yeah, so now I have a buffer now that I can move out on the pixels. I have bumped up the frequency to 16 MHz. It actually goes up to 48 MHz if you put a crystal on it. It's a bit picky when it comes to how long the off time is, because you write a 1 pulse up, and then you pull it down again, and the length of that pulse tells if it's a 1 or a 0. But then you have the off pulse, and you would think, well, doesn't take that long to get another bit to stand up. Well, actually it does. We're talking about less than 10 cycles. So, and then you can reach like 5 microseconds, and when you go above that, it goes into reset. So at 16 megahertz, this takes about something between 2 and 2.5 microseconds to get the next bit out on the ring. So initially I had like a clear file. That means I zeroed out every byte in the buffer, and then we only got 1 pixel at a time. But here I'm rotating for every update. So I'm rotating out the data.
Hello. So I thought to show you some of the code. And let's start with the beginning here. So what's new is that I have set the timer to use PLL and 6, which is the slowest PLL. So I have an 8 MHz oscillator or a crystal. So actually it runs as, it's a bit difficult, but it means that it runs at 16 MHz. I have a timer now, so these are just constants for the timer. So because I write them twice, I wanted it in one place. I have a pixels buffer of 48 bytes. Also I have a, yeah, you saw that in the other video, Galloy LFSR, or internal one. So yeah, so I can show you right now the new delay loop. It's different than what we had before. The timer is started. I can show you. And then we write some values into the timer, the high byte, because now it's a 16-bit. You can choose it to be 8-bit actually. And I clear this interrupt enable. I find that a bit strange actually, but it works. So it doesn't care about this interrupt. This is to service routine, I think. So what's important is that you clear the interrupt flag. Yeah, so I do that. And the way this works is that when we call delay, or we enter the delay loop. See, yeah, we have a go to delay loop. So we will stay in this loop until the timer interrupt flag is set. If it's not, it will just go to delay loop. So, and then it continues. It will clear the timer interrupt. If you don't do that, you get another interrupt. Or next time you get into the delay loop, it will not delay at all. So you have to clear it. And then, yeah, you set up the timer again. And go back to main. And we do everything over again. So we have two calls to LFSR external. That's the Fibonacci type. So we run that twice. And we have the data for it here. LSR, LSRG is for Galois. That's the internal type. Run that once. Then we put it out on the port. You saw we had something on the port there. All the LEDs on the port. It's not pixel ring. So. And for a while I had something called clear pixels, but now I have fade pixels. We have a look at that. So after fading the pixels, then we put the pixel out on the port. So yeah. However, this is something I thought was interesting. If this shift register, which is the Fibonacci type, and the Fibonacci type is like you can get a lot of dark LEDs in a row. You know, they scroll down, and then suddenly you may get a lot of many, and then you get just everything. Every pattern is possible. So I like that. So I'm testing the first bit of the shift register. If there's a 0, then it skips the put pixel. So therefore it will be no pixel unless there's a 1 on that bit. And then I can get like a random update event in time also. So it don't look like it updates, it's for every frame. So yeah, and here we have this is a routine that paints everything out on the, or pushes all the bits out on the ring. So, and this is old crap actually, and here too. Yeah, so let's have a look. You saw the internal stuff. You saw this. Actually, this is quite short. It's just 7 cycles, I think. It's really fast. Yeah, and then 2 ports is very boring. It just writes to the output latches. So it takes the shift register out on the output register. Output latches of the ports, and then you have put pixel. Here I had to learn indirect addressing. You can also see I am soaring together the Fibonacci and the Galois LFSR into the working register W. I'm taking only the first 4 bits and put that into R1, and the reason for putting it into R1 is because if I want to add itself 3 times. This is the same as multiplication by 3. I know this ship has a multiplication, but I didn't bother using it, so I just you know, there's a red, green and blue. So if you want to use this as like an address out on this ring, it's not actually 8 bits, it's 24 bits. So therefore time by 3, and that's the same as adding itself 3 times. Yeah, it's a little bit dirty, but it works.
This is what happens when you write from memory and you forget that every pixel is red, green and blue. So I thought I was writing correctly, but Yep.
Then we add that multiplied by itself to, or by 3 into pixels, so we get a relative address into the working register. And when we have that address that we want to write the pixel to, we put it into something called file select register. And what's that? Well, if you look in here, you have some registers called file select register. Right now it's pointing at 8D. So if you look in the file, you can see 8D, it's pointing here. So it's just a pointer. You can't access data from there. But when you have a table like pixels, you can imagine you don't have a function here. You can't say pixels plus r1 and then in the next turn r1 increments and therefore you get pixels plus 2. I mean, if you want to access this in the runtime like a table, so therefore use an indirect access instead. You issue a pointer and then you can have instructions like postinc which access the data, which actually is 0, 0 at currently. And at the same time, this is very clever because when you access this address, it will increment the FSR 0. So yeah, we can see that actually if I okay, now in a different routine, but that's okay because we have the same thing here. So we move 48 because we have 48 bytes and we want to manipulate the pixels buffer. So, and we store it for later, and then actually not sure why I did that up there. Maybe that's junk. So now we can look at FSR. It's now 6A. And why is it 6A? Because pixels is 6A. So this instruction means load a literal. That means 6A. So we can actually replace this with 6A. But you can't say R1. You can't say that. So that's why you have this pointer. So when we access this indirect file, but it's not actually stored there, it's a virtual register. So when you access it, you're actually accessing something else, and that's what pointed at here. So right now it's pointing at 6A, which is the beginning, and that's here, beginning of pixels. So let's see what happens when we rotate this one. Yeah, it changes. It means yeah, it rotated the correct address, 6A. And now this is actually the same data. It's another virtual register, but the difference is this is very clever. So when you access this one now, you actually do two things. You clear the first bit, or yeah, so the last bit, yeah, in this data cell, which is 6A, because I know it's yeah. But since you are using this virtual register, you are also incrementing FSR 0 at the same time. So that's perfect. So, and the next one is our loop variable R1, which is still 30. Now it's 2F, and if it had been 0 now, it would have been skipping this go to next loop thing and just returned. So I could do this for like 30 or 48 times, but yeah, maybe I can speed up the video. Okay, now we are at 1. R is 1. So what happens? Decrement. Oops. Yep, we are at 0. The status register has a bit or a flag which is called SED. And that SED, whenever you do an arithmetic operation, you are affecting these flags. So if the result is 0, then this 0 flag just pops up and waves in the wind. Yeah, it's not so much more to show actually. This is the update pixels. So for every subpixel, I mean the red and then the green. Subpixel, next subpixel. So it's sets up the pixels array, indirect access, and then we access it, and it increments here. We take the value from this and put it into R1. Actually, I think I could have just, instead of using another processor cycle there, I could have just said move FF post inc 0 to R1 and then drop this one. So I will try that. I'm gonna save a cycle there. You don't have this this instruction in PIC18F actually. It's only in PIC18F. So you move file to file, if that works. Then we rotate out the data on that file. Yeah, and the reason why I do this, okay, I wrote it left, so I put whatever's in, I put it into the carry, and if there's a carry, if there's no carry, then we want to write a low, and if there is a carry, then it just goes on and writes a high. And because this is a speed code thing, or I don't know if you can call it a speed code, but time really matters in here, so I have duplicated this part here. You can see in both right high and right low, because jumping around will take 2 cycles just to jump. So if you keep on jumping, you can get up to many cycles. So if it's in here, we just repeat. We have a lot of program memory, so no problem. Just fill it up. Speed is more important when it comes to writing this low-level stuff. So if you write a low, you have 250 nanoseconds between these 2 instructions. So you get a 250 nanoseconds high pulse, and here you get a 250, 500, 750 nanosecond.
And here you can see the scope, and the time base is 1 microsecond per division. And you can see, like here we have a long pulse, which is about 750 microsecond, and then a short pulse, which is 250 microseconds almost. It's a bit shorter actually. And last time I had an internal oscillator in the chip, but now I'm running with this 8 MHz crystal, and if you have a crystal you can use the PLL. So in theory I can run this microcontroller at 48 MHz. And the reason for selecting a 16 MHz was, or going from 8, is that I couldn't write from memory to the pixels without getting a dead time here that was short enough, because this here, which is about see if you pull it back a little bit there, you can see it's about 3.2 microseconds. If it goes over 5, then the ring, or all the pixels in the ring, thinks there's a reset and latch all data in, so we don't want to do that before the whole sequence is finished. So yeah, if you want to see more, we can scope. See nothing. Okay. Oops. There you go. See, we have some bursts, and they are about 50 milliseconds apart, and there's about 1.5 milliseconds to update the whole ring.
High pulse. So, and it keeps decrementing the bit counter, so it jumps to next bit. So yeah, so the code is not that hard actually. We can do, it's only the fantasies that stops us from making great things, you know. So yeah, that's all I wanted to say. It's been 22 minutes, so probably cut this down. So thank you for watching, and talk to you soon.